Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is our next problem. Problem having been chosen or selected from the same book, Modern Physics by Paul A. Tipler. As usual, we first come to its statement. Okay. The lamp shift energy, lambda wavelength shift. Okay. The lamp shift energy difference between the 2s half and 2s half and 2p half levels in atomic hydrogen is 4.372 into 10 to power minus 6 electron volt. Part A, what is the frequency of the photon emitted in this transaction? And part B, what is the photon's wavelength? And part C, in what part of the electromagnetic spectrum does this transition lie? Okay, dear students, now we come to its solution, but before starting its solution in a proper manner, we will go through a few snapshots which will help us in reaching this solution. Okay, these snapshots will provide a guideline, a foundation for our proper understanding. Okay, the first snapshot contains a table of physical constants. Okay, this table of physical constant has been taken several times in our previous problems, previous videos. So for the time being, it is just shown on screen and we do not discuss it in detail. Okay. Next snapshot is about light quanta photons. Okay, an electromagnetic wave light is an electromagnetic wave, that is light, is quantized and its quanta are called photons. For a light wave of frequency f and wavelength lambda, the energy E and momentum magnitude P of a photon are E equal to hf, photon energy. Okay, first equation, and momentum P equal to hf over c, where c is the speed of light, and this alternatively becomes equal to h over lambda. H is Planck's constant. Okay, this is photon momentum, second equation. Okay, in the third snapshot, dear students, we are seeing the electromagnetic wave spectrum range. Okay, when we study electromagnetic spectrum, we come across various ranges like infrared, visible, ultraviolet, and many other split portions of electromagnetic spectrum. Okay, however, our answer of the solution of the problem falls under this category, that is radio waves. Okay, so here we have omitted brief description of other wave nature. Okay, we have only taken radio waves. Okay, about radio waves, it is enough to describe that radio waves whose wavelength range from more than 10 to power 4 meter to about 0.1 meter are the result of charges accelerating through conducting wires. They are generated by such electronic devices as LC oscillators and are used in radio and television communication systems. Okay, this definition will be utilized in the C part. Okay, Anyhow, we first come towards part A. Part A, E is equal to Hf. H is Planck's constant, F is frequency, E is the energy. Okay. From here, if we keep frequency F on one side, then frequency F becomes equal to energy E divided by Planck's constant H. Here value of energy E is given in the statement. Okay, so we have put that value in the numerator. Moreover, the value of Planck's constant H is given in the table which we have included in our first snapshot. Okay, and in that snapshot, value of Planck's constant H has been given in two alternate systems. Okay, anyhow, we have taken one of those two which is stable according to energy in electron volt. Okay, so next to this there is just a simplification. Okay, when we divide 4.372 by 4.136, we get 1.057. Okay, into 10 raised to the power minus 6 into 10 raised to the power plus 15. Okay, because 10 raised to the power minus 15 is in the denominator, and when shifted to a numerator, it will become 10 raised to the power plus. Moreover, electron volt will be cancelled with electron volt, and we know that 1 over second or second inverse is equal to hertz. Okay, hertz or second inverse are one and the same thing. Okay, 1 hertz is equal to 1 over second. Okay, so it will become 1.057 into 10 raised to the power 9. Okay, because 10 raised to the power 15 are plus, while 10 raised to the power 6 is minus. So from 15, 6 will be subtracted and we will get 10 raised to the power 9 hertz. Okay, because as I have already said that there is no difference between hertz or 1 over second or second inverse. Okay, so here in place of second inverse we have written hertz. Moreover, we can also write this thing as gigahertz, because giga is equal to 10 raised to the power plus 9. Okay, dear students, like kilo, mega, giga. Similarly, if we go towards 10 raised to the power minus side, then milli, micro, nano, etc. Okay, anyhow, to this extent our answer is 100% correct, that 1.057 into 10 raised to the power 9 hertz. However, as a matter of discretion, in the next step we have written it as being equal to 1.057 gigahertz. Okay, now we move to part B. Part B of this problem says, in part B we know that momentum of photon is equal to Planck's constant h into frequency f over speed of light c, and this is alternatively equal to h over lambda, and this implies that c becomes equal to f lambda, or in other words, if we keep lambda on one side, then we will write lambda equal to c over f. Value of c speed of light is given in the table which was included at snapshot number 1, and value of frequency f we have calculated in previous step. Okay, so we have put both these values here. Okay, one value from the table and one value which we have calculated in the previous step. Okay, next is just simplification. When we divide 2.998 by 1.057, we get 2.84. Moreover, 10 raised to the power 8 is in the numerator and 10 raised to the power 9 is in the denominator. So 10 in the denominator will prevail, and we will get 10 raised to the power minus 1, because this 10 when shifted to a numerator will become 10 raised to the power minus 1. Into meter. However, second inverse will be cancelled with the second inverse. Okay, because this is meter per second, that is 1 over second or second inverse, and in the denominator second inverse, this is also equal to 1 over second. So second inverse will be cancelled with second inverse, and we get 2.84 into 10 raised to the power minus meter, and this becomes equal to 0.284 meter. Okay, to this extent our answer is 100% correct. However, as a matter of discretion, in the next step we have converted this meter into centimeter. So our wavelength lambda has become equal to 0.284 meter or 28.4 centimeter, and answer of part C is radio waves range. Okay, because this wavelength, that is to say, if we re-study the definition of radio waves given in the snapshot, we will fall that this range falls in the radio waves. Okay, while other split of electromagnetic spectrum like ultraviolet waves, infrared waves, etc., those will not be applicable here. Here radio waves range is applicable, and hence solution of part C is radio waves range. And this is the end of our problem. This is the end of our video. Till next video, Allah Hafiz.